Okay, great. So we'll pick up where we left off. So last time we covered a lot of territory, kind of introduced asynchronous and synchronous sequential systems. I kind of talked about that, how we can view them in multiple ways. We talked about mini machines, more machines, right? Anyone remember what's the difference between mini and more? Yeah.
The next state only depends on the current state or remote.
Next state depends on the current state. That always depends. No.
The output only depends on the current state.
Exactly. So in a more machine, the output logic function ignores the input coming to the state machine, right? So output depends only on the current state. It does not depend on the input coming into the sequential system. And the advantage of that is that changes in the input, like a spike or something, don't propagate to the output. And then there was a further special case of more machine where the output actually just comes literally from some of the bits of the state register, right? I mean, so that's a case where we called it as registered outputs. Yeah.
And any statement can be represented as a
No, multiplexer is combinational. No, you can't, right? But a multiplexer may get used in the combinational logic part of the state machine, right? I mean, of the sequential system. So sequential system, really, you can think of it as any digital system has a bunch of registers. Any synchronous digital system has a bunch of flip-flops or registers controlled by a clock, and they make up your state. And the remaining stuff is combinational logic. That's your combinational logic. And really, that combinational logic will have two parts. Some combinational logic, you can think of it as producing the next state, and the rest will produce the output. So, and that's true for any system. There is like I give you literally any circuit, you should basically be able to collect all the registers, call it the state register, and look at all the combinational logic, and then think of it as two parts. One part is computing the next state. So it's connected to input of the state register, and the other part computes the output that's going out to the rest of the world. So that's sequential system. And we analyzed it in terms of like what the truth table for that combinational logic was. And from that, we can clock by clock kind of see what was happening in the system. And then kind of I made the argument that I can also think of it in terms of a graph where every possible value which can sit in the state register can be thought of as a node in a graph, like in this figure. And then my next state function, like how I move from one state value to a new state value, can be captured in the edges in this graph. And my output logic function can be captured as, in this particular case, you kind of see that how within the bubble, we kind of say what the output values are. So it's just a pictorial representation. The key thing to keep in mind is that if I have many state bits, if I have lots of registers in my system, then my system can exist in many states, right? I mean, if I have 1,000 flip-flops, 1,000 bit worth of state, then I have 2 to the power 1,000 possible different states, and I cannot draw the diagram like this. So this strategy works only when I have a few state bits. And that's usually the case when you are doing things like protocols and user interfaces and things like that. On the other hand, if you're doing things like where you're doing arithmetic or counters or things like that, then we have lots of bits, lots of states. This is not a good way to represent things. So this strategy pictorially shows us how the system is moving from one state to another, what causes it to move from one state to another. So we had kind of discussed this. And then towards the very end, I had kind of started on how kind of these type of things we can kind of think of in 3 broad categories, and I had started on the very first one, but the 3 broad categories are acceptors, classifiers, and transducers, and I'm going to sort of walk through them today. But at some level, what you can say is my sequential system takes a stream of inputs, right? I mean, if I have a bunch of inputs, you can say at every clock tick, it takes a sample on every input and it produces a sample on every output, right? So it's taking a stream of inputs and it's producing a stream of output. So sequence in, sequence out. Acceptors are a class of sequential systems which at certain point are supposed to produce a yes/no result. So kind of the idea is that I have a sequence coming in. At some point, there is, let's say, a special character in that sequence, something indicating that now I want you to produce an answer since for the most recent input you got. So you can kind of think of it as getting characters in, and every time I get a period indicating end of a sentence or end of a paragraph or something like that, end of a chapter, then I want you to output something. And the example I had was that I'm getting English characters, A through Z, and then additionally a dollar symbol. Dollar indicates end of sequence, and whenever you get a dollar in the sequence, I want you to output whether until now in the characters that came in, was there UCLA occurring in a sequence, right? That's what we want. But many other problems have this kind of characteristic. It could be, I could say, I have digits coming in, and then every time you see a dollar, you have to tell me that if I were to think of those digits as a number, was it divisible by, I don't know, 5, let's say, okay. If I were to ask you the sequence of numbers which came in from most significant to least significant, how will you tell that it's divisible by 5? Anyway, I give you an arbitrary large sequence of digits and I ask you, is divisible by 5? Last digit. So in this case, this is an example. Clearly, I can solve it in a finite state. I only need to look at the last digit, right? If I were to ask you, and the number is divisible by 8, what would you do? Okay, so yeah, last 3 digits, right? So in that case, the memory I need is the last 3 digits, right? So these are examples. These kind of problems can be solved with a finite amount of state. Okay, there are problems which you cannot solve with remembering only a finite amount of things, but these kind of problems you can. Okay, so these acceptors, kind of the idea is they're saying, I'm giving you an input, and then at some point I'll say, do you accept the input or not? You're classifying it into yes, no. Okay, kind of a sequence. UCLA occurring in that sequence is an example of that. Okay, so the way we had approached this thing was, as shown out here, one way of approaching this thing is the following. You first think of the positive case. So I start with something, and if I see a U, I move to the next state. I see a C, move to the next state, L, A, and that's my accepting state. And then everything else is a variance from it. Anytime if I am in any of these earlier states and I get the dollar, then that means game up. I didn't see UCLA. I just get to the failed state, which is out here. Okay, and then I stay put there. And then we have things like I may get UCLA. So the thing is, we have to look for all these cases, right? I mean, at every stage, one new character comes in. Do I go back all the way to the beginning, or am I going somewhere in the middle? So let's say I got A, B, C, U, C, U. So if I get that, then the new U is possibly a start of a UCLA. So I'll go back to this state out here. So it's sort of logical reasoning. There's no general strategy to it. On a problem by problem basis, you'll have to apply your ingenuity to kind of see how you will structure it. Your question? Great question, and we are going to be throwing those kind of questions at you. So, but let's take that example, right? I mean, I want to look for the pattern A, B, A, C, right? So my good case is again A, B, A, C. Okay. Now what will happen is the following. I see A, B. So I'll get an A, I'll get a B, then I get an A, okay? And then, sorry, that way of writing. So I get an A, I get a B, I get an A, I get a C, that's the good state, right? Now, let's say after this A, at this point, I get a B. So that's a start of an AB. So then I will go back to this state. Does that make sense? So basically, this state in your example would mean I have seen AB. So again, no general strategy. You'll have to kind of figure it out. It's but that's how it works. Things like sort of where you have the same pattern repeating again and again tend to be a little bit more complicated to deal with. But so you had a great example, yeah. Okay, so you can think of these things as basically they're dividing strings of arbitrary length into two categories: strings we like, that's the pass strings, and the strings we fail. I can have more complicated examples. I can say anytime you see UCLA or USC or Caltech go to success, right? I mean, I can have options in there and all, right? I mean, or I can say anytime you see UCLA twice in the string, okay, with some arbitrary stuff in between, then I declare it, right? These are all examples that can be done in a finite with these kind of finite results. So for our purposes, though, all that matters is we are saying, look, examples where given a string of arbitrary but finite length, at the end of it, I want to basically tell whether I accept it, whether it satisfies some property or it doesn't. Okay, pass fail. Yeah, I think I have already covered it. So accepting state, rejecting state, and all. So let's look at this example. What do you think? No, sorry. Yeah. Okay. So, these are cases where given a string, I'm dividing into two categories: yes, no, pass, fail, happy, sad, whatever, right? And if any of you have done a machine learning course, that's what we call a binary classifier. Okay. The more a slight generalization of it is called classifiers, and the idea is the classifiers can end up in more than two states. So I could basically say, I give you a string, right? And then I basically say, what's a good example? Let's say it's a string of digits, and I would say, give the answer, think of it as a number, and tell me what is it modulo 7, remainder when I divide by 7. In that case, there are 7 possibilities, right? Remainder could be 0, 1, 2, 3, 4, 6. So the strings, all the set of strings can be, in that case, divided into 7 categories. So that's an example. Or it could be, I don't know, let's say strings coming in, and if you see the name of a professor from UCLA, then it's called UCLA string. From USC, a USC string, and Caltech, a Caltech string, right? So 3 categories in that case, and if none, then that's a failed string. So classifier is just a generalization that instead of 2 categories, pass, fail, or yes, no, now have multiple categories. Okay. So now this view of acceptors and classifiers is kind of like a mathematical view, or now hardware introduces some additional complications. First thing is hardware is always running. There is no concept of the string comes, it stops, and I'm doing nothing after that, right? I mean, in software, it makes sense. I give you a argument with a string of certain length, and then you operate on it, or a file of finite size. But hardware has some interesting characteristic. My sequential system is always running. I power it up, clock ticks keep coming, it's always doing something. So when you have acceptors and classifiers in hardware, they kind of take a little bit of a different form than the way this mathematical version does. And typically what you would have is the following, that these kind of hardware would have some way of indicating start of a string, end of a string, and at which point the state machine has to do something. So there is no hard and fast rule for this, but kind of the idea is that the state machine, among its input, would be the symbols that we are getting, right? Those characters of the string, if you may, the letters of my alphabet, okay? But at some, so one version could be these inputs include a special symbol $, and then on the outside, not only is it giving me the output, yes, no, 0, 1 for different classes, but then it would also give me a symbol called ready, a kind of a signal saying, okay, I'm done. I detected the $, and I have the answer. So kind of the idea is that the FSM at every clock tick is outputting something out here, but the external world will look at it only when ready is high. So in my example out here, input keeps coming, at some point $, comes, and then the ready is raised to a high value, and at that point the outside world is going to look at the out. So this kind of procedure, some sort of a understanding with the outside world, is called kind of like, you can think of it like a handshake protocol, some sort of a mechanism by which the state machine and the outside world interact with each other. This is a very simple example. There are far more complicated things that occur in real life. Like, for example, what if my input was not coming every clock tick? Let's say input came whenever the external world felt like giving you an input. So very commonly would be that there would be some other signal out here also, which will say there is a new input present. Okay, let's say some sort of another signal called whatever, valid or something like that. Okay, so the idea is that the FSM should look at the input only when there's a clock tick and valid is high. So that's an example of a handshake. There is no hard and fast rule about these. It's all these things are problem dependent. So I can't just give you a recipe, but just wanted to mention in a way that hardware world is just more complex. There are going to be these additional signals which are going to tell you when is the input ready, when is the output ready, when should the external world look at the result of the FSM, when should the FSM look at the data coming from the outside world. So, and just remember, hardware never stops. It just keeps running. So we have to do these kind of things. Yeah.
Is the output deterministic for FSM?
Great question. So FSMs, as we define are deterministic because we have no way of creating something which is non-deterministic, right? All our gates are deterministic, flip-flops are deterministic. So we can't design truly random hardware. You can fake randomness. There are so-called pseudo-random number generators. Google for it, you'll see what. But they are again deterministic. It's just that they repeat after long cycles, but they are still deterministic. To get to random hardware which will produce random numbers, you have to introduce some source of randomness. Okay, that source of random, and actually, I mean, we do need random hardware. Why do you think we may need random hardware which produces random values? Like, where is randomness useful? Okay.
Like security, like if you're
generating keys, right? If you are generating keys for your SSH or some other security protocol, you need a truly random number. So there are two ways of doing it. My chip should have some hardware, some sort of analog hardware, which can create randomness. So usually they exploit some quantum phenomenon because that's where randomness comes from. So that's one source of randomness that we can exploit. There is, can you think of some other source of randomness that exists in the world? Some other sources of randomness. And you're, someone else wants to take a shot? Or,
Radioactive decay.
okay, radioactive decay. Great one. I put a radioactive material, it's sending out alpha particle and beta, right? And then somehow you detect them and What else? Anything else that you can think of? Yeah.
Only input,
Huh?
only input.
Yeah, well, hard to exploit, but absolutely it could, although it's not that nicely random as kind of the radioactive decay, but absolutely you could. Some other examples, key presses by users on the internet, sufficient source of randomness, packets on your network, those are random, so they have sufficient randomness. So there are a bunch of examples. So actually, modern, you literally can buy random number generators, hardware random number generators, plug them into the USB port of your thing or build it into the motherboard of your computer. So you could do it. But back to your original question, given what we have studied, these are deterministic. There's nothing under it.
So since they're deterministic, can they just be replaced by an encoder that does the same thing? But since I know like given an input.
Yes and no. Okay, so the problem, if my input sequences were always fixed length, then I could, or I were to tell you maximum length, you could, right? I mean, if I were to tell you that the dollar symbol will come after at most 1 million characters, then I can design a combinational circuit which takes those 1 million, up to 1 million characters and then feeds them in. The problem, it would be horrendously bad way of doing it, but one could conceptually. The problem is here the input length is not bounded, right? We are saying keep looking at the clock ticks until the dollar symbol comes. It could be 1 million, it could be 1 billion, 1 trillion, quadrillion, we don't know what it is, right? So so what we do know is that eventually it will be finite, it's just that we don't know what it is. So unfortunately we can't, although in theory we could. Yeah. Okay, so dollar at the end of the input, at that point, this will examine things and then sort of spit out its result out here, and then also set ready to be high to indicate that we are done. Okay, so those are acceptors and classifiers. So they take arbitrary length input and produce an output at the end. The third category is kind of more interesting, and these things are called transducers. And what they do is they take a sequence in and they produce a sequence out. Okay, so they take whatever, a bunch of input symbols coming in and they produce a stream of symbols as an output. So unlike acceptors and classifiers, in principle, they are always running. So like, for example, a very trivial example would be numbers coming in, and at every clock tick, you output the sum of the preceding 5 numbers, for example. Okay, so digits coming in, and or whatever, numbers, 2 single-digit numbers coming in, and I want you to output 2-digit numbers, except with the property that every clock tick, the number at the output is the sum of the previous 5 inputs that I have received. So that is a never-ending process. I can just always keep running, and lots of examples in the world are like that. If you think about like when we process sensor data, or good example, let's say I have camera images coming in, every clock tick there is a new image, and I'm going to, at every clock tick, I'm going to output whether 1 if the image has a cat, and 0 if the image doesn't have a cat. Okay, so that's an example of a transducer. Sequence of images in, sequence of zeros and ones at the output. So transducers are never-ending process. Now, of course, finite state machine will take some time to do. So unlike combinational logic, the output will appear at least 1 clock tick later, potentially more, depending upon how much time the finite state machine takes. So that's the concept of transducer. So now let's look at an example. Output 1 if input thus far has even number of 0 bits. So let's think about it. What we are saying is I have bits coming in, and at every clock tick, I want you to output a 1 if thus far I have received an even number of 0 bits. So like we start out, receive nothing, so I should output 0. I get the first bit, let's say that bit is a 0. Well, actually, then so here when we start out, I have not received any, right? So you could argue I have received zero bits, and therefore that is even, and therefore I will output 1. But then if the first bit is a 0, then I have received an odd number of 0 bits, and so on and so forth. The key point out here is, all I need to remember out here is, thus far have I received even number of 0 bits or odd number of 0 bits. So S1 and S2 are basically indicating that have I received an even number of 0 bits or odd number of 0 bits. So this is S1 corresponds to there has been an even number of zeros in the input thus far, and S2 corresponds to an odd number of zeros thus far. That's all I need to remember. So in this case, to solve this problem, I just need 1 bit of state. How many, like, instead of counting how many zeros I have received, all I need to keep track of is the number of zeros I have received, even or odd. And then every time I get a 0, I move between these states. And as long as I keep getting ones, I stay in the respective states, right? So this is an example where I don't need all the prior history, even though looking at it like thus far kind of suggests that I have to keep track of everything. All I need to keep track of is thus far, is it even or odd? So just 1 bit of state. Another example, output 1, if the bits that I have received, if I think of it as a number with LSB being the last bit I received, is it divisible by 3? Okay, so again, so let's say I received 1, I first received a 1, then I got a 0, then I got a 1, then I got a 0, right? And so at every point, so like 1 0 1 0, when I got a 0, I want you to output whether 1 0 1 0 is divisible by 3 or not. Now 1 0 1 0 is of course not divisible by 3. The answer is going to be 0. In this case, at no point, when I got a 1, it's not divisible by 3. When I got 1 0, that's not divisible by 3. Then I got 1 0 1, that's not divisible by 3. Then I got 1 0 1 0, that's not divisible by 3. But some other pattern, right? Like 1 0 0 1 would be divisible by 3. So the way to solve these kind of problems, again, my input could be arbitrarily large. But the trick with these kind of problems, on first blush, it seems like, how can I do it? I mean, how can I take this arbitrarily large sequence and do it? But remember, what is going on is that when we say divisible by 3, really there are 3. The way to think of it is that I categorize them into modulo 3, is it 0, 1, or 2, thus far. So S0, S1, and S2 are the 3 states which correspond to number thus far, whatever that long string I have received. Its modulo 3 is 0, 1, or 2. And then, of course, if it is 0, then that means I am going to be outputting, this is a good state, so I'm going to output a 1. And in the other 2 states, I'm going to output a 0. And then we do the following. We say, let's say I have received a number, right? Let's say I have received xn minus 1, x1, x0. Let's say I have received that on the input. This is the latest input. And let's say I'm in S0. Let's imagine this number I have received, and is something arbitrary, is divisible by 3. So I'm in S0. And let's say now I get a 0. There are 2 possibilities, right? I mean, at this point, I can get a 0 or I can get a 1. So this number is divisible by 3. So it is 3 times something. So let's call it 3a. And now let's say I get a 0. So what is this new number? It is 3a shifted 1 place. So multiplied by 2, so that's 6a and plus 0. So did everyone get it, right? I mean, if I tell you that the number thus far is divisible by 3, then it would be 3 times some a. And now I get the new bit to be 0. So the new number is 3a shifted left by 1. So that's multiplied by 2. So that's 6a plus 0. So the new number is 6a. That's again divisible by 3. So I will stay put. So that explains this error. And if I got a 1, then it's going to be 6a plus 1, which would be modulo 3 would be 1. And that's why you see this one error. And so on and so forth. Let's say this number xn through x0 was modulo 3 was 2. So then I can say it is 3a plus 2. And again, I play the same game. If the new number is 0, then it's 3a plus 2 multiplied by 2. So that's 6a plus 4 plus 0. Well, it would be modulo would be 1. So that's why you see going to one state. And if it was a 1, it would be 6a plus 4 plus 1 modulo would be 2. So I kind of stay put out here. So every state you can do this thing. This kind of problem could be anything. Modulo 7, modulo 5. It's the same story. If I'm doing modulo k, then you need 0 to k minus 1. Those are the possible states. So of course, this becomes very painful if I'm looking at very large numbers. And so one of the things is if my large number is a composite number, like if I were to ask you, is it divisible by 15? So you could solve it by doing 15, or alternatively, you could say, I'm going to have 2 finite state machines. One will check divisible by 3, the other will check divisible by 5. And then if both of them say true, then the answer is true. So I can take the output of 2 state machines and then put an AND gate and work with that. So sometimes the problem is better solved by sort of having multiple worker finite state machines handling some part of the problem. So apply your ingenuity, unless there is like sometimes I may say you have to solve it with one finite state machine. Case is different, but like otherwise divide by 3 would need 3 states, divide by 5 will need 5 states, and then you just combine them, versus having a machine which has 15 states in it. So this is an example. So again, there is no shortage of kinds of problems that can be addressed using finite state machines. Pattern matching kind of things tend to be fodder for courses and all, but really in real life, finite state machines are used almost everywhere. I mean, anytime you see any sort of GUI, okay, buttons and menus and all, there is a finite state machine behind it. Anytime you see a device with buttons and all, there is a finite state machine behind it. Anytime you see a network protocol, a radio talking to another radio, they're all using finite state machines. So it's sort of they're everywhere. They're the heart of any sort of computing where you are dealing with external, some sort of an interaction with external world. So FSMs are powerful. You have a question? No,
Yeah, what a compact notation for the other graphs.
You'll shortly see. Okay. One compact notation is regular expressions. I had mentioned that last time, that these patterns which could be recognized by these sort of graphs actually correspond to regular expressions. So I can express finite state machines as regular expressions.
So I could model, for example, like the cloud architecture or something like that with regular expression.
You can model. No, you can't, but you can model these kind of problems like the pattern for UCLA as a regular expression. Anyone who knows regular expression, how would you write a pattern to detect UCLA occurring in a string? Yeah, anyone else? Anyone else wants to try regular expression? Like, how do you? I give you a string and say it should match something where there is UCLA occurring within the string. Okay. So, what am I doing?
It's particular history to say UCLA.
Yeah, or more precisely, I would say start star UCLA. Sorry. Yeah, I will say actually scratch it. Dot means any character, start 0 or more time, UCLA dot star dollar. That's how you would probably write it for the expression. Okay. Those of you have not used regular expression ever, you are missing out a lot. It makes your life super easy when you are searching for things in documents and stuff like that. Google Doc understands regular expressions, for example. So it's a very powerful thing. It has nothing to do with this course specifically. It's just a general string matching thing which exists.
So this is for any FSM or just for string matching problem?
For it will work for certainly for in our particular case acceptors and classifiers. Okay. The transducers are trickier. Okay. So now thus far we have seen kind of a very practical view of FSM, what they can do. But we also need to work with them a bit more rigorously. So FSM is as a mathematical object, something that we can reason about formally also exists. So if you go to like finite state machines Wikipedia page and all, you'll probably see something like this. So mathematically, finite state machine is some sort of an object which has 6 different things. Okay. First is there is a set sigma, which is the input alphabet. It's basically saying what symbols I can see at the input. In hardware terms, every clock tick, I'm getting an input, which is a member of this set called sigma. So it's a set of symbols. In some example, it could be like in my UCLA example, the set sigma was A through Z and a dollar. Then lambda is the output alphabet. Every clock tick, it is outputting a symbol. Okay, and that symbol comes from this set uppercase lambda. So that's the output side. S is a set of states. It's a finite set of states. Okay, let me ask you. So the system can be in one of these states. A combinational logic, you can think of it as a system which has only one state. It's always a set state. Okay, it's outputting something based on input. So in that view, combinational logic is just a extreme case of a sequential system. So S is a set of states. And in graph terms, then I can move between them. In my state register terms, I basically say if size of S is n, then I need log2 n bits in my state register at least. S sub 0, which is a member of S, is the initial state. So there is a unique start state that I have to be. When the system powers up, I will make sure that the system starts in the state called S0. Delta is the state transition function. It corresponds to my next state logic, or it corresponds to the edges in my graph. We use this notation. I'm sure you have seen it in math. Can someone tell me what it means? Delta colon S cross sigma is S. We teach it in math. I know you would have seen it.
Does it mean that S not S
No, that is up here. I'm asking about this.
cross product?
Delta colon S cross sigma goes to S. What does this notation correspond to in that? Okay, so what it's saying is delta. Okay,
It's sort of like if you take like a set of states, you have like one sort of in like go map so map it like it provides a mapping.
yeah, it's a mapping. So it's saying delta is a mapping which goes from the set, which is the cross product of the set S and sigma. Now, what's the cross product of two sets? If I give you two sets, let's say a set 1, 2, 3, and another set A, B. What's the cross product of the set? No one knows. Well, I do know some good questions for my next quiz. It's going to be math review. But in this case, when you take cross product of two sets, you look at every possible combination of elements from the two sets. So this would be a set which would consist of 1 comma A as one member, 1 comma B as another member, 2 comma A as another member, 2 comma B as another member, 3 comma A as another member, and 3 comma B as another member, right? So it's all possible combinations. And then it is mapping them back to state. So what is this saying? In our example, it's saying take a state and take a member from S and take a member from sigma. What is sigma? It's the input alphabet. So it's saying for every state and for every input value, tell me what the next state is. So this is the current state and this is the next state. So it's saying for every current state and every possible value of input, what the next state is. It's basically telling you the entry in that truth table for next logic, next state logic, or alternatively the edges. That's what it is doing. It's just a succinct mathematical notation. And finally, omega is the output function. It's basically going to say for every state, and if it is a Moore machine, it will say for every state, what's the output? And if it's a milli machine, it will say for every state and every input combination, what's the output? So omega depends. If it is milli, omega would be a mapping from current state and current input to an output. And if it is Moore, it is simply going to be a mapping from state to output. So I can think of FSM as a collection of these 6 things: a set sigma, a set lambda, a set S, a state S0, and 2 functions, delta and omega. And given these, I can I have all the information I need to say what my FSM does. The reason this matters is that tools, like for example, like if you use a tool which, given the state diagram or creates hardware, it inside software, it will maintain a data structure capturing this kind of information so that then it can reason about it, it can work over it. So mathematical representations are super important, just like we saw Boolean algebra to reason about combination logic. FSMs, we work with this kind of a structure, these 6 things together define an FSM, and then our software tools manipulate these things. So let's see now how we can map FSMs to sequential circuits. Let's work with those. So there are variety of ways to approach this thing. Firstly, if you have access to a tool like Verilog, you can just write code in Verilog and it will create the hardware. It will figure out what the state machine is. Then there are tools like FISM. It's a tool dedicated to designing finite state machines. So there you draw these diagrams with edges and all, and then you push a button in their user interface and it outputs Verilog. And then you take Verilog and then it creates hardware for you. So today, like designing FSMs is super easy. If you are a software person and you want to write software corresponding in FSM, again, there are tools for that. You write your user interface description as a finite state machine, and there are tools which will generate whatever Python code, C code, whatnot and all. Okay, so FSM is so super useful. Your regular expressions that I was describing, that's what they do. When you write a regular expression, basically some software takes that and creates a finite state machine in order to then sort of produce some code and which does it. So, so in real life, there is a sequence of things that we kind of go on. You kind of describe your FSM in some manner, and then kind of gradually, eventually, it produces some netlist, some set of gates and all to do your job. We are going to do it manually. Okay, so what's the step sequence that we are going to follow? So let's say I want to do that. I want to create a finite state machine which given which does the following. Its output goes high for each third cycle that the input is high. Okay, so what I mean by that is if I get 1, 1, 1, then output is high. And so let me explain from this diagram out here. It's a little bit. Every time I get 3 ones, then I want to output a 1. So for this group of 3 ones, this one got output. The next group of 3 ones, this one got output. This group of 3 ones, this output. So kind of the idea is I'm counting how many I'm basically every time there's a new group of 3 3 ones have happened, I'll output a 1. You see that my output is delayed by a clock tick. Why do you think that's happening? So like we had this group of 3 ones, and then the output is delayed, is happening in the next clock tick. Okay, I'm going to call on people. Hi, you with the phone, looking at the phone? Hello, white t-shirt. Sir, can you attempt to answer this question? Why are you in the class if you are just busy with the phone? Did you hear what I was talking? You are welcome to leave and come back when you have time.
No, I still.
Okay. Please pay attention. I mean, it's kind of annoying, right? I mean, I'm lecturing and kind of you're busy with your phone. Okay. Anyone wants to? Why do you think there is a delay in the output appearing after I have recognized that there are 3 ones, right? I mean, if you notice out here, there is this group of 3 ones, but the output is happening in the next clock tick. Something with the hardware, right? I mean, what is it saying that what kind of finite state machine would it be if output is taking is only appearing in the next clock tick and not immediately? Yeah, because it's a more machine, right? I mean, so this timing information is saying something about like what kind of machine it is. If it was a mealy machine, then input would immediately affect output. Okay, so this is suggesting that perhaps we are leaning towards more implementation. Faced with a description of the problem, it usually you would have to kind of decide, am I looking at a mealy situation or a more situation, right? So this is just one of those examples where it's kind of nudging us towards a more solution. So first thing we have to do out here is we have to decide in this problem, what do I need to remember about the past? How many states do I have? So, and how do I move between these states? And then what are the outputs in these respective states? So let's think about this problem, right? We are basically saying, whenever I see three ones, I want to output a one. So there are 4 possibilities here. I have not seen any one. I have seen 1 1, I've seen 2 ones, and I've seen 3 ones, right? So no ones, 2 1, sorry, no ones, 1 1, 2 1, 3 1. So those are 3 states: 0, first, second, third. Okay, so I'm sort of 4 possibilities. And then every time I see a 1, so in is true, I go left to right. And as long as I see not in means I'm seeing n equal to 0, so I cannot stay put, right? So every time I see a 1, I go from left to right, and until I reach the third one. And at that point, there are 2 possibilities. I get a 0, in which case I go back to saying I've not seen any ones, or I get a 1, in which case I go back to the first stage. And then output is 1 only in the final stage. So that's what we'll be doing. It's another pattern, right? I mean, the pattern here, instead of saying UCLA, is saying anytime I see a pattern which is 1 with a bunch of zeros, another 1, a bunch of zeros, another 1, then output a 1. Okay, and then every time such a pattern occurs, output a 1. So that's what's going on out here. So we, with these kind of problems, start with drawing the state diagram. What makes it different than if this was a purely software problem was that we have to worry a little bit about timing out here, right? I mean, because we're going to map it into hardware with clocks and stuff like that. So, so that part is okay. Now what we have to do is we have drawn our we draw our state diagram. I'm going to skip these things. Okay, we draw our state diagram. You're not responsible for these slides because this has to, and then we are going to make a circuit from that. So let's pick kind of a problem which is a bit more tangible and see how we'll walk through the whole thing. So let's say we are designing a very simple traffic light controller. Okay, so what we have is the situation that it's an intersection and there are traffic lights as shown out here, right? There is east-west direction and there is north-south direction. And I have 6 traffic lights, right? I mean, this the traffic lights in vertical direction would be the same, and left-right direction would be the same. So there are really 6 traffic lights we're controlling. So let's say the goal is I want to design a system which will control these traffic lights. And we are given some requirements out here, and we'll see how to walk through. So usually when faced these problems, they're going to, in some natural language manner, they're going to describe to you some constraints. So it says traffic light should reset to green in the north-south direction. That's requirement number 1. So it's basically saying when the system starts up, it should be green in the north-south direction. Then the second one is a safety requirement. It says if the light is green or yellow in one direction, it must be red in the other direction. So it's okay to have both directions red, but it can't be that I have green or yellow in one and green or yellow in the other also. So that's a safety requirement. Third one says a light must be yellow between changing from green to red, much like it happens in common light, right? When it goes from green to red, temporarily turns yellow. Okay. Then it says, and remember here we said it's green in the north-south, kind of by default when it starts out. And it says, if there is a car waiting in east-west, then east-west should become green, and then it should become yellow, and then go back to red, and north-south should become green. So it's saying if there is a car waiting on the east-west, and to do that, we have a sensor. So we have these sensors sitting there, which basically tell us whether there's a car in the east-west direction. So basically, we are saying this is kind of one of those intersections where the main road, north-south, has priority, but whenever a car comes in the side road, then the sensor detects the car and then turns the right. Okay, so north-south direction is always green. It's the major street, but whenever the sensor reports it's an east-west thing, then we have to do something. So this is why you see that there is an OR gate, which is basically saying it's combining the output of the two sensors and saying there is something on east-west. So finite state machine is going to look at that, do its job. There is a clock signal, there is a reset signal, and then I have to control the lights, and I have 6 lights: red, yellow, green in north-south, and red, yellow, green in. So usually this is how problems are given. They are not given in those truth table or state diagrams and all. You will be given problems in this manner. I'm talking about like in real life, right? I mean, that's some customer is going to describe requirements in this particular manner, and your job is to really kind of parse these things. It's very much how software also works. Your customer is going to give you requirements, and then you have to parse them and kind of figure out what should my software do. It's the same thing. You are given some requirements, and sometimes they may be ambiguous, in which case you are conflicting, in which case you go back and ask or apply common sense to kind of resolve these issues. Okay, so in our case, this is what we are given, and we are going to develop a finite state machine starting from that. So let's do that. So firstly, a finite state machine consists of states, inputs, and outputs. So inputs and outputs are clear out here, right? I mean, I have outputs controlling the 6 lights. Input is the input from the sensor. So those are given, those are kind of obvious from the problem. Really, the state we have to figure out. So let's think about how many states are there. Now, north-south light can be in 3 states, right? Red, green, yellow. And east-west could be in 3 states, red, green, yellow. So first thing you would say, oh, there are 9 possible states, right? 3 for left, right, 3 for vertical. But not all those 9 states are possible, because why not? Right. That was the constraint, the safety constraint we had, right? I mean, if I am in green or yellow in one direction, I have to be in red in the other direction. So that eliminates certain states. So in this particular case, if you think about it, there are really 4 states that the system has, which is green in north-south, yellow in north-south, green in east-west, or yellow in east-west. Red is implied, right? So I truly have only 4 states in my system. And which state is the starting state? Reset state. It's green in north-south. So this state is the starting state. So 4 states decide this. And input is clear. There are 2 inputs. There is car east-west sensor and the reset sensor. And output are controlling the 6 lights. And we can basically say that we like depends on how your lights are, but probably a reasonable thing to say is that it's in some sort of one hot vector. So I can think of it as 3 bits controlling the north-south and another 3 bits controlling the east-west. Okay, because only one of those lights can be on. So within a cluster, so it's a one hot thing. So I can basically think of it as 2 groups of 3-bit one hot coded stuff. So at this stage, what we are doing is we are kind of just figuring out at a high level what my finite state machine looks like. Next step is, remember, finite state machine had those 6 things, right? It had the starting state, we know that. It had the set of states, we know that now. It had the set of inputs, we don't know that now. Set of outputs, we know that now. What are the 2 things missing from our view of what a finite state machine had? It had 6 things, right? So we have captured 4 of them: starting state, set of states, set of inputs, set of outputs. 2 things missing. What are those? the two functions, one which tells us how do I move from state to state, and the other which tells me given a state and inputs, obviously, what output do I need to get. So that's now you have to design. But again, we have all the information out here. We were given all the information, so we're going to work through that now. So let's see how that works. So what we do is we kind of lay out our 4 states. So we are now the 4 states, we can just give them the name corresponding to what is happening. So we call them state 1 is GNS, stands for green north south. YNS, yellow north south. Green east west and yellow east west. The names of the states should probably reflect something about the problem so that someone looking at that can make some sense out of it. Now let's talk about what the output should be. That is kind of straightforward, because if I am in green north south, then north south should be green, and green should be turned on, and for east west red should be on. If I'm in yellow north south, then yellow should be turned on for north south, and red should be on for east west. Again, remember, we were representing my output in this manner: green yellow red for north south and east west. And so for each one of the states, output is easy. And finally, we have to decide, how do I move from state to state? So when I start out, we start out in GNS. So kind of the idea is that whenever reset comes, wherever I may be, I should go to GNS. Okay, so if there is a reset signal, go to GNS. That's the default. And then as long as reset is true, or there is no car on the east-west, I stay put there. Then, so our alternative is that reset is false and there is a car on east-west. If that's the case, then I have to cycle through the east-west loop. So I'm going to go to yellow north-south because I've returned the light yellow. Then I'm going to move to green east-west and then yellow east-west and then cycle back, as long as reset doesn't happen. So this is basically kind of describing a very simple and almost stupidly simple state machine, because it's not that, I mean, all it is going to do is going to turn the light green for 1 clock cycle and yellow for one clock cycle, which is probably not enough for any car to go through, but let's imagine that that's the situation. So it's kind of just doing that. So in this simple model, given that plain English description, I was able to come up with this kind of a state diagram. So we now have a full-fledged thing. Our 2 functions are really kind of embedded in this diagram. This is the hardest part when faced with these kind of problems, really are figuring out what your states are and making this diagram. Okay, these are the 2 crucial steps, because figuring out how many states, what the states are and all is really where kind of your understanding of the problem comes into play, and likewise figuring out how you are moving between them. The set of inputs, outputs, and start state, those are kind of relatively obvious from the problem. So once we have this machine, yeah, we have already done this. Once we have this machine, we are going to make actual hardware out of it using flip-flops and combinational logic. So in order for us to do that, since we're take time and we are at 5:09, so let's take a 5-minute break. And so we'll move to this next step. Given a diagram like this, how do I create the hardware from that? Okay, and we'll see that. So let's again, so we'll start at 5:14.
Out of curiosity, if I were to model like a LangChain agent, for example, as a state machine, a mathematical notation would
all that the user gives it would be the input alphabet and the output alphabet, and then we'll figure out of this set of tools that it has like all the other parameters.
Yeah, so output in that case would be something which is what tool to activate at what point in time. So if you have n tools, then you have n possibilities, right? So LangChain basically would say, okay, in what order to activate the tool. So you can say my output alphabet is the tool name.
So the set of tools are my omegas basically.
Set of tools is your lambda. Actually, sorry. That's
Omega is the
lambda, right?
output function. Like in
Is my Greek bad?
on the FSM as a mathematical index slide.
That's not omega, that's lambda.
Oh, that's lambda.
Yeah.
Oh, that's
Yeah,
omega.
that's omega.
That's- looks like W. W is omega.
No.
It's like that's lowercase omega.
This is lambda.
Right.
Second one, output alphabet.
I'm talking about the output functions.
Oh, you're talking about output function.
Yeah, yeah,
Okay, 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 okay.
Yeah, so like are the tools the output functions?
No, so the output function is going to tell you which tool to activate in any step. That's the output function,
Okay.
right? Whereas lambda is telling you the name of the tool, right? I mean,
So I'm providing the lambda of the tools.
you have to provide all the, you're going to provide the lambda, which is a set of tools. Yeah, and then your state machine is going to walk through the states and it's going to out which tool at the state level.
So how about like for the end user, like when they type a prompt, which part of the state machine are they providing in that case?
Well, in a way, they're providing the prompt is the input, right? Now, of course, in that particular case, there is a what is really happening is that neural network underlying this is taking the prompt and is then producing the input to a state machine. That's the way to look at it, because the neural network itself, you won't model it as a state machine, although it is a finite state machine.
Is it also determining the output alphabet simultaneously from the prompt? Because I'm saying what I
Yeah,
have and what I expect.
Exactly. So it's doing a lot more. Firstly, FSM is not this is too simplistic a way to think about complicated problems. Okay, because so I won't do it, but concept in theory you could, but
Yeah.
but it's not. There are papers which look at those neural networks in terms of finite state. Okay, but that's more of a mathematical exercise.
From a very high level, like, can we say like it's basically doing
It is it's a deterministic exercise, absolutely. Yeah, very high.
the reason I'm looking at it this way is because I'm trying to make a program that could like create FSMs for different applications using natural language. So,
Actually, they can already do it. I mean, you can query ChatGPT to write an assessment. Absolutely, in Verilog.
but it won't like it's not very robust. So I'm trying to.
Yeah, it's probably not very robust, but you can certainly do it. Yes. And actually, you can even ask it to create these kind of diagrams.
Is there a way to optimize FSMs is there like an algorithm for that?
Yeah, just like we have logic synthesis, you have it for assessment.
Can this be used for cloud optimization?
For putting in the cloud optimization.
Like, for example, let's say I want to create an architecture for some certain application. Like, can I use optimization methods for FSMs on my architecture to make sure that it's as lean as possible?
You can use it, yeah, absolutely.
Is there a
There
tool
are-
already that does it?
Yeah. There are FSM optimizers, yeah.
No, like specifically for cloud.
I don't know about cloud, but like for hardware and software usage and all that, of course. Yeah. Yeah. Okay,
All right, thanks.
sure, yeah. Okay, let's see. So let's assume, so what we have is a diagram at this point. In this case, we made this diagram given some specification in plain English. In some other cases, you may already be given this, right? Sometimes what happens is there are standard bodies or other companies and whatnot. They create these diagrams based upon sort of separate standards for network protocols and all. And so you already have this kind of a diagram, and your job is to implement it in software. At other times, you're creating a system from scratch, in which case you will create these diagrams from some plain English. Be what it may, at some point we have a diagram like this. So now we are going to work with that. Now, what we are going to do here is we are going to first simplify the diagram a little bit. So if you go back out here, this diagram is a little bit cluttered. And the reason it is cluttered is because of the reset signal, right? What is happening is wherever we are, if there is reset, we go back to the left state, right? I mean, if you look at all these weird edges which are going, they're really handling that case that we are basically saying if reset, immediately go to the state GNS, it doesn't really matter. So this kind of reset, usually it is easier to just factor it out so that we can focus on the main part of the problem. Okay, it's kind of like in processors, we have a reset signal to just reset the processor, hardware takes care of it, it immediately just makes your processor jump to a particular address in the operating system. So we are going to simplify that machine just so that we can focus on the main part. So we'll just assume now that reset is 1. If reset is 0, some special hardware will make sure that I go to GNS. Okay. So now what we are left with is the state machine as it looks like out here. We are basically sitting in GNS as long as there is no car on the east-west direction. If there's a car on the east-west direction, I go from GNS to YNS and then unconditionally cycle through GEW, YEW, and come back to GNS and then repeat the process. So this is basically we are assuming set equal to 0. Okay, and reset equal to 1, we are going to just handle it separately. Very commonly done just to sort of simplify things, and in hardware also you will do this. So now faced with this, from this diagram, we can first create this kind of a table. So this table is basically capturing the 2 functions that we care about, the next state function and the transition function. Next state function and output function. So I have 4 possibilities of the current state. And then I have only one input, car east-west. So if car east-west is 0, or if car east-west is 1, depending upon that, my next state is decided. So for example, if I am in GNS and car east-west is false, then I stay in GNS. If on the other hand, car east-west is true, then I move to YNS, which is this state. In YNS, GEW and YEW, I don't care about car east-west. So here you see these pairs are the same. So this is my omega function, right? It's basically telling me, given the current state, what next state to move to. It's the next state logic. One thing I've noticed is that I'm still talking about states as if they were names. I'm not telling you what bits correspond to those states. And that's for a very deliberate reason, because it's a choice we have. You can do it many different ways. How many bits do you think we'll need for the states here? State register, how many bits should it have? 2. Yeah, at least 2. Okay, so there are 4 states, so I need at least 2 bits, but depends on how you code the state. If I do one hot coding, I'll need 4 bits. If I do something else, maybe some different number of bits, but at least 2 bits I will need. Okay, now we also have to worry about the output, and that's written outside out here in this diagram. So you kind of see my 6-bit output. We see that. So you can literally think of them as wires going to the 6 lights. Okay, 1 means turn on, 0 means off. Okay, and the first 3 bits correspond to the north-south, and the second 3 bits correspond to the east-west. Okay, so from the diagram, I can create a table like this. Now you begin to see something which kind of looks like my sort of truth table type things. So I can sort of play with that. So, but before I do that, I have to figure out how do I represent those states in terms of bit. So this problem is called state assignment, and it's all I know is I have 4 states, and therefore all I know is that I need at least 2 bits, but nothing about the problem yet tells me what bits to give to what states. So this encoding is a very important choice. Tools which work with finite state machine, they try to optimize this coding. They try to see which encoding would result in a smaller hardware, for example, or a faster hardware or a lower power hardware. So the encoding is super important. Now, here we have a toy example, so things don't matter as much, but in complicated examples where you have thousands of states, that's super important. Now, typically there are two very common strategies for assigning states: one hot or binary. Okay, so one hot is obvious, and binary is the compact thing, right? So in our case, it would be a 2-bit thing. It still leaves a lot of choice, right? If I do 2-bit, I have 0, 0, 0, 1, 1, 0, and 1, 1. Which one should get what is not very clear. Let me just ask you. So let's say in my diagram, which state would you assign? Let's say I decide to go binary state. So I have 4 possibilities: 0, 0, 0, 1, 1, 0, 1, 1. Which state will you give 0, 0, 2, and why? Why? Yeah, and why would you do that? No, it's the reset part. Remember, whenever there is reset, I want to go to 0, 0. My flip-flops tend to have the reset signal. So it's very easy in hardware to globally reset every flip-flop. And so if I make my default state to be the one which corresponds to that, then my life is simple. Okay. So if I'm using binary encoding, then putting all zeros to the default state is a reasonable thing to do. Other 3 patterns is less clear. Should I give 0, 1 to YNS or GEW or YEW? We don't know, and there is no strategy there is no guaranteed strategy, because this is again one of those problems which is NP hard. There is no, short of searching for every possibility, there is no answer to it. Okay, so let's try some mapping. So it turns out if you are doing things manually, one-hot coding actually is a lot easier to work with. If on the other hand you are using some tool, then binary coding yeah, you can work with that. But for manual design, one hot is usually simpler. Okay, so let's say we decide to do one hot coding. So what we do is we have YNS, GNS, these 4 states, and I give them these 4 encodings that are sitting out here. So I kind of assign them. So GNS is 100, 0100, 0010, and 001. So 4 possibilities. Okay. Okay, so now let's see how we can build hardware using the diagram that we had and using this state encoding, that GNS, YNS, GW, YW are like that. So the way we do it is, for this one-hot coding is, think of as if for each state, I have a flip-flop, corresponding flip-flop. So we do that. We start with, we just put down a flip-flop, and kind of the idea is one of these flip-flops will have the value 1 and the other will have the value 0. So that corresponds to my one-hot coding. So this is the GNS flip-flop, this is the YNS, GW, and YW. They are basically indicating if YNS has a 1, that means that I'm in the state YNS. Okay, and the other 3 will have to be 0. So we start by putting these down, and then of course I have the 6 lights. So now, firstly, looking at this, you can easily see how can I control the light. Let's say I've asked you control the green light north-south. So, well, looking at this, we see that the green light north-south is controlled, is high when I am in the state GNS. So the green light for north-south can just take the output of GNS flip-flop. Right? It is 1 only then. What about the yellow light? Yellow light is 1 for north-south when I am in this state. So there is a 1-to-1 there is a one-to-one mapping between some of the lights and some of the flip-flops. What about the red light for north-south? Well, the red light for north-south is 1 under 2 settings. So that's like an OR gate. Either I am in GW is high or YEW is high, then the red light is on. Or alternatively, you can say red light is high if green and yellow are both off, right? So there are many. So output logic is with this approach is kind of some simple combinational logic. The transition part is the trickier one that we have to handle. So let's say I am in the state GEW. Then that means that GEW is 1 and the other are 0. Right? Let's say I'm in state GW, this state. Next clock tick, what do I want? Next clock tick, I want to be in YEW unconditionally. So I just need to move this one into the next flip-flop. So you can say output of this guy connects to this guy, because the 1 will move there. Likewise, when I'm in YEW, the 1 has to move from this guy out here, but there's going to be some additional complexity we'll shortly see. If I was in YNS, it will move like this. And if I was in GNS, I'll move to YNS, but again, with a little bit of complexity. So there is some rough strategy emerging that in a clock tick, I'm going to take the output of one flip-flop and affect the output of the neighboring flip-flop. So let's see how it works out. So if I am in GW, I always go to YEW. If I'm in YNS, I always go to GEW. But GNS is tricky. In GNS, if sensor says there is no car on east-west, then I stay put. So there are a variety of ways I can make GNS 1. One is I was in YEW, and next clock cycle, I will go to GNS. So that's one case. So OR gate, I get this part. Or alternatively, there is no car. So that's the bubble. And I'm already in GNS. So that's the AND gate. So this AND gate is saying, I'm already in GNS and there is no car. Then again, GNS is 1. So this little combination logic is basically capturing that structure, that there are two ways I could enter GNS. So that's the OR gate. One says YEW, so that was the bottom one, and the upper one is I am already in GNS and no sensor says false, and that's the other one. And then I move from GNS to YNS if sensor says yes. And so that part, and I was in GNS. So this AND gate is capturing that. So usually for problems like these, given this with one hot coding, you can kind of manually just draw it out in logic. So for like just looking at this and kind of just follow like when am I moving from one state to another? Anytime there are more than one way of moving from into a state, that's an OR gate. Anytime those edges have some condition, that will indicate an AND gate. And you kind of just draw things out like that. So that's the advantage of one hot coding, that going from diagram to circuit is super easy. The disadvantage is I need 4 flip-flops. I need as many flip-flops as number of states. So it's arguably wasteful. On the flip side, though, it's perhaps simplifies the combinational logic. So you may come out ahead, right? I mean, it depends on how costly is a flip-flop relative to a AND gate, for example. Flip-flops are bigger, no doubt. So our state transition got taken care of. Any questions on this? Any that how I drew this one? So again, things to keep in mind. If all I have is an unconditional edge from one node to another node, that's just a straight wire. So we had this, we had this, and there was no other entry point. If a state has 2 or more ways of entering it, 2 or more incoming edges, that means there is an OR gate. And anytime an edge has some condition on it, that means an AND gate. So So this edge out here has a condition on it. So that's why I have an AND gate. I'm basically saying move to YNS if GNS is true and car east west is true. Okay, and so on and so forth. So so make sure you see why each connection in this logic was justified. But the claim I'm making is that kind of looking at this diagram, you should be able to draw this kind of a circuit in one hot coding. So just one-to-one mapping. Output is similarly very easy because, as I said, red, green, and yellow lights just come from the states. So this green light is just coming from GNS, and this yellow light is just coming from YNS. And red light is saying I'm neither yellow nor green. And likewise, I do the same thing on the other light. So even the output becomes super easy in this particular problem. So we can do this thing. Now, the only thing is here we assume that reset was not taken for, right? I mean, now here we do have a problem, which is my GNS state is not all zeros. So when I reset, I have to do something more clever about it. So either I can use flip-flops that have a set function in it. Okay, so I can say when I start out, I want GNS, when the reset signal comes, then I say set GNS and reset the other three flip-flops. So I could handle that way, or I can add on to it the reset signal to this logic, okay, which I won't do, but one can modify that. Okay, so I've kind of walked through this one. And if you kind of build this thing, it's kind of a logism realization, it kind of works. There is logism, the flip-flops have both set and reset, so one can conceivably sort of work with that. Okay, now let's say I don't want to use one hot coding. Let's say my flip-flops are super expensive and I want to reduce the number of flip-flops. So at that point, doing it manually is, other than the simplest of the problems, is not an easy way to do. So now you'll have, firstly, you'll need to optimize the combination logic, but also the other thing is we have to figure out how to assign the states, right? I mean, so I have 4 possibilities, 0, 0, 0, 1, 1, 0, 1, 1, and I have 4 states. So I can assign any to any. How many different ways do you think I can assign the states? So I have 2-bit state values and I have 4 states. How many different possible ways of assigning bits to state exist out there? 4 factorial, right? I mean, I can, for GNS, I have 4 choices, for YNS, then 3 remaining, and then for GW, 2 remaining, so it's factorial 4 choices. So there are factorial 4 different ways of assigning states. This is why this problem is hard, right? Because if I have 100 states, that's a bad number, let's say 128 states, so that means I will have 7-bit numbers for the state, and I will have 128 factorial ways of doing it. Factorial is a very rapidly growing function, right? I mean, so it sort of grows very rapidly. So the state assignment problem, assigning it so that my eventual hardware would be very efficient, is extremely complicated. The only thing you can do is to, for these small problems, try out all factorial 4 possibilities. So that's 24 possibilities, and then see which one works the best. Now, one help out here is GNS is a default state, so it makes sense to give it 0, 0, but then I'm still left with factorial 3, so 6 possibilities. I'm still going to try them out. Okay, so let's see how we work with that. So now I have encoding. So I take those encoding and I plug it back into that table I had created some time ago. Yeah, several slides ago. this table. In this table, we only had symbolic values for the states, names for the states. So what we are doing now is we take literally just take that table and we plug in the state values now. Now I have a truth table. This is an input. These are inputs. And then I have two functions. One is the next state and one is the output. You have a truth table written in a funny manner. So you can now create the combinational logic for this thing. One easy way of creating the next state logic in this case is using a multiplexer. So let's say I say you can use a multiplexer to make the next state logic. The way we can approach this thing is I can say, okay, give me two 4-to-1 multiplexers, and then I can work with that. Okay. Or give me two 8-to-1 multiplexers, because there are really three inputs, two state bits and the Kari's bit, and I can work with that. Okay. Output, there are 6 output functions corresponding to 6 lights. So I will also have to create those. So let's walk through it. So let's say that two next state bits are NS1 and NS0. And I have 3 inputs, Kari's, twist, and then S1 and S0. So I have really 2 Carnot maps, one corresponding to these bits, and the other corresponding to the other 2. Okay, so I kind of fill those out. I have 2 Carnot maps there, take care of that, and do the usual game. That's the cluster there, and this is the cluster here. I write down the equations. NS1 is simply saying S0, and NS0 is S. Kind of, you work it out. That's the equation. So I just apply my Carnot map type stuff to kind of do it. What about the output? It's more design, so it depends. It's independent. Output in this case is independent of Kari's twist. So I can write down the equations, and kind of just looking at it, you can write down the equations. So we end up with this as my implementation of the state machine. Just at this point, all we are doing is we're just designing some combination logic, and this is how the gate looks like. So this is the alternate design. In this case, we have 2 flip-flops and a combination logic, which is a little bit more complicated to work with this. Okay, so that's our design in Logisim. It works. You can write it in Verilog. Those of you know Verilog, that's also there. So I have now 2 designs. One hot-coded, where I needed 4 flip-flops and a few gates, and the binary one where I have 2 flip-flops and more gates. Looking at this, given that a flip-flop is of this type is around 10-12 NAND gates equivalent. So by eliminating 2 flip-flops, I'm saving a lot of gates. So the second solution is probably significantly better, but doesn't have to be always like that. So anyway, so the big advantage of one hot is manual design is easy. You can write code, you can write your own code to kind of do it. It's just that there isn't a whole lot of optimization opportunities. The second one is dealing with a harder problem. Assigning those state bits is not tricky, and it's not clear that I couldn't do better than this. Maybe one of those other 5 solutions are better, but I don't know. I didn't try them, but those are possibilities. Okay, so that's how we approach this thing. So the process is natural, plain English description of your problem. You figure out the usually input output is kind of obvious from the problem. You'll have to figure out what my set of states is, just in terms of names, right? And which one of them is the starting state. Then you have to figure out how do I move from state to state. At that point, drawing the diagram is the easier thing. And what do I output at different states? So state diagram is the way to go. Then after that, depending upon your state encoding strategy, one hot versus binary encoding. You kind of follow this mechanistic process to kind of get down to the solution. Now, at some stage, I got sort of tired of sort of working with these things myself. So I wrote down a tool which I tried last year, where you give the diagram to it using graph language, which is very commonly used, and then it generates a Logisim state machine for you. So I kind of automated that process. So I'm going to introduce that to you guys, so that you can focus on the part of the problem which is more relevant. Now, the only thing is, when I implement it in Logisim, I don't implement it in terms of gates. I use a ROM. Why do you think I use a ROM? Anyone remembers what a ROM does? Huh? Yeah, it's a read-only memory, but why do you think, why am I using a ROM to implement the finite state machine? Okay, I think all of you guys have already forgotten. You are dancing around the right thing, but not quite. Yeah. No, nothing to do with FPGA. ROM is just a table where you give if you make the address to be your input and the content to be whatever output you want, then you can implement any combinational function. So all I need to do is, if you give me a state machine where, let's say, there are 2 inputs and 3 bits of state, that's 5 input. I pick a ROM with 32 addresses and sufficiently wide, I can implement anything. So it's super easy to implement combinational logic using ROM. It's a universal blob, okay, to implement combinational. So that's how I kind of end up doing it. Now, of course, in real life, one won't do it. ROM is a very expensive way of implementing combinational logic, but it at least gives me a pathway to kind of go from concept to a functioning system and do something with it. Okay, but in real life, you'll use some logic optimization like what Logisim provides or PyEDA provides. Okay, so thus far what we saw is one aspect where we have something to optimize, right? Namely, what bits to give to different states. Second thing is the combinational logic part, the next state logic and the output logic. There we apply standard combinational logic optimization. There is a third place where optimization is often needed. So we humans are very bad at thinking about states. So sometimes what happens is that we create state diagrams, but where the states are actually redundant. I could reduce the number of states. So that's this notion of equivalent states in finite state machine. And kind of the idea is that even before I attempt to synthesize my thing, I have to first see, it's kind of like saying, am I using an efficient algorithm or am I doing unnecessary stuff? So equivalent states in finite machine is a concept that in the state diagram, some of the states may not be necessary. And can I get rid of those? So kind of the idea intuitively is, we'll say that 2 states in a sequential system in my state diagram or in my digital circuit are are equivalent if we cannot tell them apart in the input-output sequence. What I mean by that is, let's say my system was running and it was in some state I. And then whenever it's in state I, let's say at that point, I just replace I with J. Okay, the state whose bit pattern was J. And I keep running the system, and if no one noticed, for all possible inputs, no one noticed, then that means I and J were the same. So kind of they are totally equivalent from a perspective of the observer. So consider 2 systems, N1 and N2. Okay, they're just the names of the systems. which are copies of the same state machine. But they start in, one starts in state Si and the other starts in state Sj. Okay, so they have two state machines. The state machines have, each state machine has a state called Si and a state called Sj. And let's say what I do is the first system N1, I just make sure that t equal to 0 is that it's in state Si. And the second system N2, I just make sure that t equal to 0 is in state Sj. And I feed the same input to both of them. And if the outputs are the same, that means Si and Sj were equivalent. I cannot tell them apart. So that's the notion of equivalence, right? There is no way to tell them apart by just looking at the output. And therefore, that means there is some redundancy in my state machine. So, yeah, okay. So we apply same input to both, and we end up getting the same output, and we do it for every possible same input. Okay, in the sense that we are looking at the claim will say that whatever be the input sequence, however long, whatever, there is no point you can tell them apart. So if the outputs are the same, we can say they are equivalent, and more formally, we say Si state Si is equivalent to state Sj if for every possible input the two produce the same output, assuming we started in Si versus Sj. Okay, so now of course this is a mathematical definition, not very useful because I can't certainly not try with every possible input. So I need to find some better way of finding that two states are equivalent. So how do we do that? Kind of a notion is there is this theorem which says Si equal to Sj if and only if, and this is a recursive definition, if for every input X, every single input X, the outputs are the same and the next state is the same. So it's kind of saying two states are the same if for every possible input they produce the same output, not input sequence, every possible input symbol, they produce the same output, and the next state is the same. Next states are equivalent. Okay, so this is a recursive definition, but intuitively, if you think about it, it makes sense, right? I mean, if I have two states, and when let's say the input is A, they give the same output, and they go to two states which are equivalent, and then I'll have to prove that. So if that's the case, then these two states are equivalent. So the advantage out here is I'm no longer looking at all possible input sequences. I'm only looking at all possible inputs. Much simpler problem, right? I mean, all possible input sequences, they're infinitely long sequences. So that's an infinite space on the infinite set, but set of inputs is finite. So that's a very powerful thing. There's no proof that I'm giving to you, but at an intuitive level makes sense. Two states are equivalent if I cannot tell their behavior apart, and they're moving to states which are equivalent. You have a question? Yeah, so you'll see that. So next lecture. Okay, indeed. So you'll begin to have clusters of states which are equivalent to each other. Absolutely, great observation. Okay, so I don't think I'll start on this today. This will take me more. So what we are going to do is we are going to systematically identify sets of states which are equivalent, as he was suggesting, and then replace them, merge them into a single state. Okay. And it turns out that a lot of stuff that we design has these kind of redundancies. So the very first thing in a complicated system we do is to minimize the states. Okay, so that we have a more efficient state machine. And then after that, we do all that bit assignment and stuff like that and all. Okay, so we are going to look at it next time. We are going to do it in context of this particular state machine, but it looks horrendously complicated, but actually a lot of states here are.
Good question.
Good to meet
Cloud
you.
architecture can that be viewed as being a chance to research?
Actually, again, you are saying the LangChain one, right?
Not LangChain, no, like cloud architecture. Like, for example, you have an architecture